All right, in this explainer, we're going to dive into a pretty profound scientific mystery. We're going to explore how modern science literally lost and then eventually found the ability to ask the question, why? For over a century, the dominant scientific dogma insisted that correlation alone was totally sufficient to understand reality. What we're going to trace the historical evolution from simple probabilistic reasoning to true causal reasoning and explore how some simple diagrams, along with counterfactual thinking, form the very foundation of intelligence itself. To really understand this journey, we have to first look at human nature. In the Book of Why, Judea Pearl points to this ancient exchange from Genesis, where Eve responds to God. Just notice the instinct at play here. Humanity possesses this hardwired, deep-seated drive to establish blame, consequence, and cause and effect. Early on in our evolution, we realize that the world isn't merely a collection of dry facts. It's an intricate web of relationships. We don't just casually observe what happened. We absolutely demand to know why it happened. And yet, despite this deeply human instinct, we face a bizarre piece of history. How exactly did the founders of modern statistics systematically erase the concept of cause from scientific inquiry? For over a century, the idea of causality was treated with intense suspicion by the scientific establishment. It was considered this nebulous, unscientific concept, something that maybe belonged to philosophy, but definitely not mathematics. So how did such a crucial part of human reasoning get locked completely out of the laboratory? Well, the erasure happened chronologically, and it was driven by some of the most brilliant minds of their time. Back in the late 19th century, Francis Galton became absolutely fascinated with correlation. You know, how one variable relates to another. His disciple, Karl Pearson, took this even further. By 1911, Pearson had completely dismissed causality, dogmatically claiming that data is all there is to science. Full stop. To Pearson, causation was just a fetish. Later, in the 1920s, a geneticist named Sewell Wright tried to introduce causal path diagrams, but his ideas faced immense resistance from a statistical establishment that had basically declared causal questions fundamentally off-limits. The origins of this scientific dogma stem back to Francis Galton's 1888 proceedings on correlations. This singular focus on association rather than intervention created a century-long limitation. It actually gave rise to a mantra that gets chanted in statistics classrooms all over the world. Correlation is not causation. And while that's technically true, it acted as a massive roadblock. It essentially paralyzed fields from economics to sociology that desperately needed to navigate the actual real world. However, there were some major cracks in Pearson's edifice of a causality-free science. The biggest problem was something Pearson himself even noticed: spurious correlations. It's actually relatively easy to find correlations in data that are just plain silly. But without a theoretical, causal model, science couldn't mathematically distinguish between a highly meaningful effect and the totally spurious correlation. If data is all there is, and two things correlate perfectly, how can you mathematically prove that one isn't causing the other without stepping outside of the data itself? The short answer is, you can't. The crucial point here is the contrast, beautifully summarized by Judea Pearl. Statistics, in its traditional form, is essentially static. It provides a highly accurate history of past events and past observations. But causality, that is dynamic. It's the science of how past events influence the future. It's all about understanding the underlying physical mechanisms, so that when conditions change or when we actively intervene in a system, we can accurately predict what's going to happen next. Section 1. Mapping reality. Nodes, arrows, and DAGs. So how do we bring dynamic, subjective causality back into the objective realm of mathematics? The breakthrough required scientists to make a subjective commitment and draw a picture of their assumptions, a directed acyclic graph, or DAG. Notice how elegantly a causal chain can be mapped out. We intuitively know the season affects whether it rains, rain makes the pavement wet, and a wet pavement is slippery. Turning on a sprinkler also makes the pavement wet, but notice there is no direct arrow from season to slippery. The graph explicitly shows the influence is mediated. It structures our knowledge before a single piece of data is ever analyzed. Now, these graphs eventually evolved into what are known as Bayesian networks. They are a genuinely revolutionary mathematical tool that allowed scientists to visually draw out relationships and account for confounding variables. Instead of dealing with a massive, unreadable table of probabilities, a Bayesian network decomposes large, complex systems into smaller, manageable chunks based purely on their causal relationships. This is actually the mechanism operating behind the scenes in a lot of technologies we use today, from spam filters to medical diagnostics, allowing machines to reason through massive amounts of uncertainty. But the true power of these networks emerges when we distinguish between seeing and doing. Traditional statistics is all about passive observation,
just seeing. If I see that the pavement is wet, I might infer that it rained, and therefore infer that the season is probably fall or winter. But causality is about active intervention, doing. If I physically force the pavement to be wet by dumping a bucket of water on it, I shouldn't suddenly infer that it's winter. My action broke the natural causal chain. Standard statistics just completely lack the vocabulary to tell the difference between those two scenarios.
To solve this, Pearl introduced the do operator, and this was a profound mathematical shift. It provided a formal notation for external intervention. Standard probability asks, what is the probability of y given that we observe x? The do operator asks a fundamentally proactive question. What is the probability of y given that we actually do x? It mathematically erases the incoming arrows to a variable, simulating an intervention in the physical world. This finally gave scientists the mathematical language to express what happens when we manipulate a system, like administering a brand new drug or changing a public policy.
Section 2. Ascending the Ladder of Causation. Pearl synthesized all these concepts into a philosophical framework for reasoning, which he calls the ladder of causation. It's a three-tiered hierarchy that categorizes our ability to process information. Down at the bottom, rung 1, is association. This is pure observation, just asking what is. Rung 2 is intervention. This involves active manipulation, asking what if we do something? And at the very top, rung 3, lies counterfactual reasoning. This requires imagination, asking what if things had been different? Was it the aspirin that cured my headache, or would it have passed on its own? As Pearl points out, counterfactuals have a particularly problematic relationship with data, mostly because data are facts about what actually happened. Counterfactuals require us to reason about alternative realities that never existed at all. We obviously can't go back in time and not take the aspirin just to compare the results. Yet this ability to imagine alternative pathways and ponder what could have been, that is the absolute hallmark of human intelligence. It's exactly how we learn from our mistakes and adapt to entirely new situations. Section 3. Causation and the AI future. When you view this deep intellectual history through the lens of modern artificial intelligence, it reveals some pretty profound limitations. While AI is undeniably powerful, Pearl argues that causal explanations really should be the cornerstone of machine intelligence. Current AI models are incredibly sophisticated, sure, but they fundamentally operate as massive pattern-matching engines. They are phenomenal at taking dry facts and finding correlations. But as the history of statistics just showed us, correlation is merely the first rung on the ladder of cognition. Because of this, current AI systems have significant causal blind spots. They rely almost entirely on observational data. They process massive amounts of what is. Consequently, they're incredibly weak at hypothetical reasoning and adapting to completely novel situations. Without structural causal models, without that internal whiteboard DAG of how the world actually works, AI remains securely stuck on the very first rung of the ladder of causation. It can observe and associate brilliantly, but it doesn't truly understand why. So let's leave off with this final, provocative thought. Can a machine ever truly be considered intelligent if it can't ascend that ladder? If it can't imagine alternative realities and ask, what if? The causal revolution did way more than just fix statistics. It provided a mirror for our own minds. By restoring why to science, we're left with a profound realization that true intelligence isn't merely processing the facts of the world, but mapping the invisible threads that tie them all together.